Other than that, no worries. Other than that, there have also been proposals based on positing parity or CP to be good symmetries in the UV. Then, as you then as you run down to lower energy scales, somehow they need to be broken so that you get the standard model properties where both of these are violated. So I won't be talking about them. I mean, one thing I'll notice here is that they're still interesting, but you do have to model them a little bit to explain why these are good symmetries in the UV, they're broken in the IR, but still you get order 1 CKM phase while having a small theta bar. So that mechanism or that feature has to be built in these sort of models. So rather, I'll be talking about this other candidate, which is Axion, and we'll see that by itself it provides a very minimal and elegant solution to the strong CP problem. And at the same time, because there's a light particle, this is something we can observe in various experiments. So that's also interesting because it gives us an experimental target. So how does it address the strong CP problem? Well, it says that in the presence of the axion, the theta bar it's not just a random parameter, but rather it's a dynamical quantity and it can vary. So in more detail, what the axion does is that it couples to gluons in this particular way. And as QCD confines, that confining dynamics, it generates a potential for the axion. So you can parameterize that, or you can compute that potential. It is some periodic function. You can approximate that as a cosine. So what then happens is that if you have this cosine potential, which I'm drawing here, then as the universe goes, the axion would, even if it starts at some random point, it would relax to basically the minimum location. And in this location, the effective theta bar parameter in the presence of action, which is this combination, is dynamically driven to 0. So even if you started with some non-zero effective theta bar in the very early universe, just because of the dynamics of the theory, you in the very low energy experiments on in the very low energy universe, you are led to a scenario where this effective parameter is vanishingly small. So in this way, in the presence of the action, you can dynamically explain why theta bar is such a small number and why we haven't seen neutrality so far. So from that sense, in that sense, actions, I mean, they represent a very elegant and minimal solution to the strong CP problem. However, if you look at it from the UV, there are issues. It's not so elegant. And one potential issue goes by the name of the axion quality problem. So let me quickly illustrate what that is. And the rest of the talk will be based on scenarios in which the quality problem can be. So because an axion is a light pseudoscalar, you can model it as a goldstone that is housed inside a complex scalar field. So the complex scalar field I'm denoting by pi, it's typically called the Pidgeot scalar, and axion sits in the fields because it's a goldstone. Now, we typically expect that gravitational effects, they violate all global symmetries, including this global U1 Pidgeot symmetry. What that implies is that you can write down Planck suppressed operators of this type in a Lagrangian. Now, because this is a U1 violating operator, if you write it in terms of the axion using this parameterization, then you would notice that on top of the QCD generated potential, which is this one, you also have a contribution to the axion potential of this type. So here, this term is coming literally from setting phi to f, and then taking care of the phase factors, which appears here. So now here's the problem. Suppose you have this term, but then now you also have this contribution from this Planck suppressed operator. But then if these contributions are large enough, if they swamp over or if they dominate over these contributions, then there is a potential danger. Because what can happen, so here's what I'm just drawing these two things pictorially here. So in blue, I'm still showing the QCD generated potential, and in red, I'm showing the Planck surface contribution. So the point is, these Planck surface contributions, they need not necessarily align with the QCD generated potential. So, and if they dominate over the QCD generated potential, then what will happen is that as the action tries to relax, instead of relaxing to the strong CP solving minimum, it will relax somewhere else. However, at that point, generically theta bar won't be a very small number, but rather it will be order 1, and then you're back to square 1 because the strong CP problem has reappeared. So just to summarize, if you really want to solve the strong CP problem, in some sense, you also want to control these sort of corrections. You have to explain why they're not there at all, or why, even if they're there, they're suppressed. So of course, all of this depends on how big these contributions are. And here is where the priors on the action mass comes in. So normally, when we think about actions, we think of them as very light particles, like of the order of like EV or milli-EV or even lower masses. And for those masses, FA has to be pretty big because of various existing astrophysical and also terrestrial constraints. So now if you put in these numbers, you'll notice that this contribution is not that small unless the n appearing here is larger than 9. In other words, what it means is that you have to forbid all these higher dimensional operators up to dimension 9, and the violation appears only at dimension 10 or higher. So somehow you have to arrange for that. And this is the statement of the quality problem. So we are somehow saying that the phase-shape symmetry is somehow of such a high quality such that you cannot write down any Planck surface operator before dimension 10. Okay, so this is the statement of the quality problem, and therefore for the rest of the talk, I'll be thinking about scenarios in which you get to address this problem. So let me illustrate this again pictorially about the possible ways in which you can address this problem. So first thing to notice is that, so here I'm just repeating the same figure from before. So in red, there's the Planck surface contribution, and in blue, there is the QCD generated contribution. So the point is the QCD generated contribution near the minimum, it just goes like a quadratic function, just the mass square times the field square. So you immediately notice that raising the axion mass itself, it basically raises the blue curve here, which means that it can then fight better against this against this Planck surface contribution. So that goes in the good direction. So the conclusion generally is that keeping everything else fixed, just raising the axion mass itself, it helps with the quality problem, just because you're strengthening the axion potential. The other handle depends on this other parameter that we have, which is the axion decay constant. And then depending on what kind of FA values you have, there can be very distinct possibilities. So first, let's imagine that FA is of the order of the gut scale, some unification, maybe the unification dynamics or the unifier theory, maybe that also gives rise to an axion, and that's how the FA is. So for those values, you immediately notice that these corrections, they are actually very, very big because FA is now not that small compared to the Planck. And then you are in much, much bigger trouble because these contributions are large. So if FA is in this regime, somehow you have to construct scenarios in which you forbid all these terms absolutely. Like you literally say that they are absent or they're extremely suppressed, maybe by some exponential factor. So that is something you have to do if FA is so large. On the other hand, if FA is much smaller, maybe of the order of like TeV to PeV, just to take some example, then you already notice that this FA over M Planck ratio that keeps appearing, that is much smaller, and then you naturally suppress these sort of contributions. So for the rest of the talk, I'll be focusing on these two possibilities. So first, I'll focus on gut scale FAs, and I'll construct this. I'll give some example of a scenario in which you solve the quality problem and you explain why these dangerous operators are not there. And then as an observable, we'll see that the axions could be a decaying dark matter candidate, which can lead to X-ray or gamma ray signals. In the second part, I'll be thinking about like this much smaller phase. And because the phase is now much smaller, you can actually produce these axions and do a resonance search in the context of various beam dump and other collider experiments. So broadly speaking, so these will be the two parts of the talk, and I'll focus on each of them in turn. All right, so let me now discuss this case of large FA. So as I said, we are thinking about very high limits, right? So these corrections are very large, and we need to just forbid these sort of corrections. So one possible way in which you can forbid these terms is that if you imagine that the actions, they are not fundamentally, they are not scalar fields, but rather they arise from some U1 gauge fields in some extra dimensional theories. So the way this works is the following. So let's say you have a 5-dimensional theory. So along with the standard 4 space-time dimension, you have another extra spatial dimension. And let's say you have a gauge field in this extra dimensional field. So because the gauge field would need to have 5 components, there is a standard 4 components, which would constitute like a 4D vector in low energies. But then along with that, there is also the 5th component, which I'm denoting by A5. And if you look at the gauge transformation of this entire object, you'll notice that A5 basically walks and talks like a scalar. It behaves as a scalar under gauge transformations. So what happens physically is the following. If you are resolving the extra dimension, or if you are probing the theory at energy scales larger than the inverse size of the extra dimension, you get to see the full gauge field. But if you are at energies where you cannot resolve the extra dimension, then all you see is this vector particle, a mu, and some scalar, which is A5. So far, the story is just whether you are resolving or not resolving the extra dimension. But the good thing that happens is that you cannot write down anything you want in terms of A5, because in the fundamental theory, A5 comes from a gauge field, and the 5-dimensional or the higher dimensional gauge invariance that protects the Lagrangian for AN automatically protects the Lagrangian for A5. And this is the feature that ends up suppressing these sort of contributions. You just cannot write down the operators that I was writing down a few slides back. So that is the primary idea, that gauge invariance protects the potential for A5. And that's how you can address the problem if a phase so large. All right, so A5 would be our potential candidate, but then you will immediately ask, well, I mean, we do want that. We do want the action to talk to the standard model. After all, that's the thing with which we can search for it, and that's how it's going to address the strong CP problem. But it turns out that there's a very elegant way of writing down the standard AGG dual operator in this 5-dimensional theory. So because you're in 5 dimensions, you can construct the 5-dimensional elliptic symbol, and then you can write down an operator in which a U1 gauge field couples to some non-abelian gauge field that lives in the bulk of the extra dimension. And then if you go through the algebra, it can still give you this non-shift symmetric axion coupling to these gauge fields. So this appears, but then of course the other dangerous contributions, they do not appear. So in that sense, you really can think of A5s as the axion. All right, so this has been a toy example, but then while I'm not a string theorist, this is very, very similar to what happens in explicit string theory constructions. So the idea is that in string theory, you of course need many extra dimensions, definitely more than one. And then if you have these multiple extra dimensions, you can have multiple ways of compactifying these higher dimensional analogs of these gauge fields. And that can often lead to not just one axion, but rather like order 100 axioms. So just to give you some motivation, like these kind of ideas, they are all motivated from the UV, and they can be formalized within this Axiverse paradigm, where the upshot in some sense, or the generic conclusion, is that you can have axions which are uniformly distributed on a log scale, so their masses can really vary. Their masses can be light, but can also be heavy. And typically, if you do not have complicated geometries, or if you do not have warping, you expect the FA to be around the gut scale. So this is just to give some UV motivation of why you expect heavy actions, and also why you expect gut scale FAs, and how the quality problem is solved in all of these contexts. All right, so I won't be, of course, talking about string construction. So I'll take a much simpler field theory viewpoint, and then ask or construct explicit examples in which actions get heavy. So what I'll think about is a scenario in which you take a standard model and you imagine that at some high scale of the order of the unification scale, the standard model gets unified with a dark SUN gauge group. And that is what the action couples to in the UV. So you have the standard coupling here, but then instead of coupling to QCD only, it couples to this larger gauge group. Now, as you come down to lower energies, this gauge group, the gauge invariance breaks down, and then you have a separate coupling to standard model, and also a coupling to this dark SUN. So what is important is that unification, of course, you also need to make sure that like the theta bar running in some sense is not dangerous enough, such that the same theta bar appears for both the sectors, and whenever axion solves if you want the strong CP problem for the dark sector, it automatically solves that for our sector as well. So unification in that sense is playing a big role, because it relates the theta bar quantity for both the sectors. All right, so now how does the heavy action arise in this context? The point is, if this dark SUN is going to confine, typically I'm assuming a Fermion spectrum which is consistent with that. If it confines, and if it confines at an energy scale larger than the QCD scale, that would basically lead to an axion mass which is much larger than the QCD axion mass, because MA times FA would be determined by this confinement scale squared, which is by construction is much larger than the QCD confinement scale. So this is how heavy actions can actually arise with gut scale FAs in the context of these unified scenarios. Now, how heavy can that be? Well, it depends. Pretty importantly on what the confinement scale is. And as we know from our QCD knowledge, it depends on dimensional transmutation. So you start with some UV scale. And then there is the standard exponential factor that determines the confinement scale. It depends very sensitively, of course, on the rank of the gauge group here, and the coupling that you have in it. So what I'll assume is that I'll assume this UV scale to be of the order of gut scale, because that's when the two gauge groups separate and they start running on their own. And for alpha UV, or the gauge coupling in the UV, I'll take a value which is consistent with just the supersymmetric expectation. But of course, these numbers, they can vary. So just for illustration, if you fix this, you'll notice that the confinement scale, it varies a lot. Of course, there is this exponential sensitivity. So depending on whether you have SU2 or SU5 for this dark gauge group, the confinement scale could be like order of like 10 to the 6, 7 GeV, or even much higher for this SU5. And then we have the confinement scale. So finally, to get to the axion max, you have to put a prior on FA. And what I'll assume is that, as I said, gut scale FAs. So for that, if you just go through the algebra, you get a scenario in which you have MED scale actions for this SU2 example, and much heavier actions for this SU5 example. Why I'm talking about such a heavy action will be clear in a few slides. I'll briefly mention the motivation for such heavy masses. But the broad point is that the exponential sensitivity leads you to a very broad range of spectrum for the masses. All of them are heavier than the standard, but depending on the mass, they can have different observational implications. And this is in some sense a toy scenario to keep in mind why in the context of the Axions, you expect a broad spectrum of masses. The same sort of exponentials, they also appear there. All right, so as I mentioned, we'll be thinking about how these actions could be a dark matter candidate, and therefore we need to investigate how they're produced in the first place. So, so a standard production mechanism for action is the misalignment production. So what it says is the following. So here I'm just drawing the quadratic approximation for the action potential. And the point is, during inflation itself, the action is very light. So its mass is much smaller than the Hubble during inflation. And that is why it is basically stopped on its potential through Hubble friction. It is not able to move significantly. And it is stopped at some value which you typically expect to be some order one number times the scale of the potential, which is a thing. So that's a typical expectation. Now, as the universe keeps evolving, when inflation ends, universe reheats, and maybe you get this radiation-dominated era, eventually Hubble falls below the axion mass. And at that point, the Hubble friction is not sufficient enough, and the axion starts doing the oscillation. So it oscillates around the minimum, and you can show like the axion energy density. It dilutes as scale factor raised to the -3. In other words, it has the same scaling as the dark matter. So this is how, like, this is a standard mechanism, which is called the misalignment of production of producing actions and explaining why they can be dark matter. And you can go through the computation to compute the relative density of these actions in terms of the FA and the MA, and you get an expression. All right. So now what's the problem? Well, the thing is, like, if you look at these numbers closely, then you would notice that if you put MEV scale action masses, as I motivated a few slides back, and gut scale FAs, then that would basically say that the actions, they overclose the universe by orders of magnitude, unless you tune this misalignment angle to be very, very small. So that's bad news. And I mean, of course, I mean, actions are motivated from the perspective of solving strong CP. So if you are doing some tuning to explain the dark matter abundance, that becomes less exciting. So ideally, you want to look for a scenario in which you do not have to do this tuning. So naively, this is bad, but the point is, we have been a little bit too quick in terms of computing the action abundance. We have to ask why the action is heavy in the first place. And the answer, as we know, is it is coupling to a confining gauge group. And the point is the confining gauge group itself, that sector can play a non-trivial role as the universe evolves, and that is going to have an effect on the action abundance. Okay. So let me briefly mention at a qualitative level of what can happen if you have a confining gauge group. The point is, this gauge group confines, and if the temperature of the universe reaches the confinement scale, that's when confinement happens, and you form hadronic states. Given the MA and the FA, you can relate the confinement temperature to those parameters in this way. Now, in the absence of light fermions in the dark sector, what will happen is that as this confinement happens, you'll form bound states of dark gluons, which are also called glue balls. And because all of this is happening in a dark sector, and because there are no light fermions, they do not have anything else to decay into. So they would tend to be long-lived. And because they dilute like matter, soon after their formation, they would take over the energy density of the universe. And you will naturally have a scenario in which you have an early matter dominated era, dominated primarily by the lightest global state, which is the 0++, where these are the quantum numbers of this global state. Of course, we do not want this matter dominated era to continue forever, because we do need to explain BBN. So these guys needs to decay into standard model before BBN so that you transition to standard cosmology. So again, pictorially, this is what will happen. This is what we are imagining. So after inflation, you reheat both the standard model and this dark SUN, and they can easily have comparable energy densities. Then when you reach the critical temperature, confinement takes place and you form blue balls. And soon after their formation, they take over the energy density of the universe, which I'm plotting along the vertical axis. And you will get this matter-dominated era where the blue balls dominate the energy density. And then after a while, they decay and you reheat to a standard radiation-dominated cosmology. And this happens at some temperature region. So the point is that you can already expect now, as this guy decays, there is entropy dilution, and that is going to dilute the action abundance. And eventually you end up with a scenario in which you explain the dark matter abundance. So I'll just like to mention that this is in some sense a bit different from what is often considered in the literature, where the blue balls are assumed to be all of dark matter. This scenario is not that because we're assuming the blue balls to be decay before. All right, so let's just plug in some numbers. So what I'll assume is that the blue balls talk to the standard model using this operator. So this is a dimension 6 coupling, and using this coupling, you can compute the heat temperature in terms of this mu scale that we need to put in, and the blue ball mass, which is related to the axion mass and the axion decay constant. The summary then is like with all of this entropy dilution, you can compute what is the axion abundance at the final endpoint. And the point is, if you allow yourself to reheat above BBN, then you can actually explain all the dark matter abundance properly for that scale phase without doing any sort of tuning in theta. Okay, so that's one punchline, that here is a scenario in which the same physics that makes the axion heavy also leads to blue ball domination and leads to entropy dilution, and that can explain the dark matter abundance. Yeah.
Could you go back to the previous version out of the abundance?
Yeah. Yep.
So the one that you have now, inserting matter domination, it doesn't depend on the axion mass at all?
Exactly. It's a good observation. So it does not depend on the axion mass at all, assuming that the oscillations start in the matter-dominated era. And the way to understand this is the following. So the initial abundance is like ME squared. But then, so after that, you have to take into account the redshift. But in a matter-dominated era, so the redshift is always like scale factor to the -3. So if you write it in terms of the Hubble, it becomes like basically Hubble squared. And the oscillation starts exactly at the point where Hubble is ME. So basically there is a cancellation with the action. And that dilution stops only when you reheat, because that's when you transition to radiation domination, but that is insensitive. So that's how basically you become insensitive to that mass. Of course, if the action oscillation starts during radiation domination, there will be some residual effect. All right, good. So that's one punchline here. So without any sort of significant fine tuning of theta, you can explain the dark matter abundance. Now, what is also interesting is that in this regime, if you compute the axion lifetime into a pair of photons, you notice that the lifetime is in an interesting range. So for again, that scale of phase and order MEV scale actions, the lifetime is of the order of 10 to the 28 seconds or so. And that is exactly the range that is sloped by various decaying dark matter structures. So note that this is like 10 orders of magnitude larger than the age of the universe, but that is precisely where the sensitive decaying dark matter structures are operating. So here's in some sense the money plot for this heavy action dark matter idea. So here what I'm talking is the action mass on the x-axis and the lifetime, the dark matter lifetime, if you want, on the y-axis. And it is all these gray shaded areas. I'm just plotting the existing constraints. They come from various surveys like Dixon and Newton. integral, comptel, new star, so all of these. And in this green region, I'm plotting the region that is consistent, like in all of these green regions, you can explain the dark matter abundance. And at the same time, ensure that the heat temperature is above 5 MeV. So BBN is not spoiled. And the subregions, they are basically for an increasing set of stringent cuts in some sense. So the big region is when the global decay operator has to be bigger than 10 to the 13 GeV with some restriction on the initial misalignment angle. So if you literally say you do not want any tuning at all of theta, you can also go to this regime where theta is constrained to be bigger than 0.1 as opposed to 0.01. That of course reduces the parameter space. And but still there are regimes which will be probed by future experiments. So talking about future experiments, I'm also showing the projections that you can have for example, from Athena mission or Theseus, which has a bunch of different instruments like SXI, XGIS, both this and this. And also AMEGO, which is another proposed MUV scale mission. So just to summarize here, the point is in this green parameter space, you explain the dark matter abundance, but at the same time, these sort of parameter spaces will be constrainable by future KP to MUV scale missions.
I think this is like, what's the observable here? Is it like just a diffuse?
No, just a line, like a couple of monochromatic.
You're just looking like where you
yeah, good. So
where just like the diffuse cameras.
Yeah. So right. So we are actually looking very close to the galactic center. So for this analysis, we did 5 degree by 5 degree galactic center. Yeah.
So this is basically a non-thermal scenario we're studying. But I can set it up using any other marathon patient. I don't need this issue. Will it affect any of your like later?
Yeah. Right. So if you're thinking of a scenario in which you have the axion, but the axion still, but the matter domination comes from some other. Yeah. So I think in some sense, like you can still have this sort of parameter space. That's totally fine. It's just that your parameter space in some sense gets widened because for the global story we have very few parameters, right? Because if you wanted to, for example, compute the heat temperature, it depends only on the global mass and this dimensional full scale lambda. This guy is not independent from any energy. You can just compute it. This is in some sense a new addition. So if you want, in terms of dimension full parameters, you have MA, FA, and this global operator. But if you have some other, maybe some other moduli decides to matter dominate, that's totally fine. It's just that you in some sense have to explain a bit of why exactly that is. I mean, it's not directly correlated with MA. It's coming from some other sector.
Also, this 10 to the 7 GeV depends on what kind of groups you are using. Like, for example, it could be your I think AC2 confining scale.
Right. So this itself, I mean, it does not depend super sensitively on the rank, because so in other words, of course, like it depends on what parameter you are fixing. If you fix MA and FA, then M0 plus or M0 plus plus, it does not depend very sensitively on the rank. But of course, M0 plus is primarily determined on the confinement speed. So once you fix that,
not the confinement space.
Yeah. That is of course there. That's
so
true.
that means you have some freedom.
Yeah, that's right.
So you have a freedom here, you have a freedom at there. So that means at the end,
yeah,
probably to collect all the freedom together, then it would be similar to non-thermal.
Yeah, it could be, except I mean, here everything is phrased in terms of MA and FA, and that is primarily coming from this one.
So if you fix the confining group,
yeah,
probably the story is that.
Exactly. Then you have very, very less. Yeah, that's true. All right. right, so this is the scenario in which you have this heavy decaying dark matter, and it gives additional motivation for carrying out TeV to MEV scale gamma ray or X-ray missions going forward in the future. So I just like to show as an example that because you're repeating so low, you might worry about what is happening to the barrier asymmetry, because when you do this entropy dump, it will also dilute the variance. So I won't be going over the details at all, but in our paper we do have a scenario in which under the spontaneous bariogenesis paradigm, where you produce lots of asymmetry with axion coupling in the beginning, but then when you take into account this entropy dump, you get to the correct level. So long story short, it's possible to explain both dark matter and baryon abundances. I'm very happy to chat about it if you're interested. And there is also an example SU8 unification story, just to make sure that all of these different fields, they can all be embedded properly. So here I'm just imagining standard model unifies with the dark SU3 to get to SU3. So I won't be going over the details at all for these two stories, but I'm very happy to chat more about this. All right, so let me now switch gears. So we have been thinking about large FA regime, but as I mentioned, if FA is small, in some sense, you do not have to talk, or you do not have to necessarily imagine that there are extra dimensional scenarios, because if FA is so small, it would naturally suppress these potentially dangerous FA over implant scaled operators. So those will already be suppressed, and that is good news from the perspective of the quality problem. So here the observable would be, because FA is now not so large, you can actually produce these states in terrestrial experiments, and you can look for them directly. All right. So what I'll assume is that you have a heavy action, and the mechanism would be very similar to what we had already. So you have some dark SUN coupling that confines and makes action heavier than usual. So I'll just assume that the heavy action is given to me, and then under that assumption, I'll just parameterize the action coupling to various standard model gauge bosons, and also action coupling to leptons. So a couple of points are important here. So I'll focus on a scenario in which you have action DUNE coupling, and that is primarily motivated from the strong CP problem perspective. But depending on whether you have this coupling or not, the physics of these heavy actions are still very interesting, and people here like Bhaskar and Julian, they have, along with other people, they have worked on this action photon coupling scenarios in which they can still produce actions in beam dump environments and then look for using similarity. So in some sense, the parameter space is pretty rich, and depending on what couplings you have, the production mechanisms and also the decay channels, they can be pretty different. So overall, I think a broad search is kind of pretty useful in terms of catching the reactions. The second point that I wanted to make is that, so here what we are doing is that we are turning on flavor diagonal and flavor universal leptonic coupling. So the reason why we do flavor universal and flavor diagonal is because, of course, you can turn on a flavor non-universal coupling here, but then that is already going to be constrained by various FCNC searches, for example, like rare muon decay modes or rare meson decay modes. At the same time, you can also turn on core couplings, but that's also going to induce FCNCs. So what we are trying to do here is to focus on a parameter space that is not severely constrained by FCNCs. But then we are going to argue that that sort of a parameter space can still be constrained using the ideas that I'll be talking about in the next slide. Okay, so complementarity with standard FCNC searches are basically the guiding principle. All right, so let me very quickly illustrate what the action can decay into when all of these couplings are present. So a few facts are important here. So because we have the action DUNE coupling, it induces mixing with standard model mesons like like the pions or the etas and eta primes. So that plays an important role in determining the action lifetime. So here in dotted green, I'm not sure how well you can see it, but here I'm basically plotting the lifetime into a pair of photons. And you see these bumps, these are basically from this resonant mixing. Of course, you should not trust the regions very near the bump because the thing is basically going on shell and the perturbative treatment of mixing is breaking down. But this is just to give an illustration. And these sort of mixing, they also play an important role in producing these actions because the dominant production mechanism would be a production of standard model methods and then them mixing into actions before reaching to your detector. There are also other important channels, especially the di-muon channel that I'm showing in dashed purple. So it turns on above this kinematic threshold and then goes on like this. So you'll notice that before the hadronic modes dominantly turn on, these axions to 2 muon channel can be significant, and we'll quantify it in the next slide more precisely. Other than that, there are also various exclusive channels like 3 pions, eta, pi pi, or pi pi gamma. These were computed recently in this paper, and there are also other references which computed this. The interesting point is that if you look at the right y-axis, you'd notice that for a phase of the order of TeV or maybe hundreds of TeVs, you typically tend to have macroscopic decay lengths ranging from like a meter to hundreds of meters. So what that means is that after getting produced, actions can really travel a large distance before decaying into this sort of final state. And that's going to be a crucial factor in detecting these heavy actions. All right, so let's just investigate the muon mode a bit more closely. So here again, I'm just plotting the lifetime of the actions as a function of the action mass for 2 benchmark values of the electron couplings. And again, just to repeat, you notice this macroscopic decay lengths can easily arise if you have these sort of effects. But then more importantly, if you just look at the branching ratio of the action into a pair of muons, you'll notice that for most of these mass range from 0.2 to 1 GeV, you would tend to dominantly decay into a pair of muons, depending on these 2 benchmark choices of electronic coupling. And I just to get a sense of the numbers here, I'm still using this notation here, and I've set all the gauge couplings to equal to 1. So compared to the gauge couplings, the electronic couplings are somewhat suppressed, and the reason being, if you literally do order 1 gauge coupling, the actions would be less long-lived, so they would have a harder time reaching the detector. So somewhat smaller electronic couplings would be, in some sense, the ideal scenario in which you can probe these actions, and that can easily arise in reasonable 2D conditions. All right, so with that, I'm going to focus on a set of different experiments, but just as a schematic, let me focus on how we can detect these heavy actions using muon modes at DUNE, for example. So the idea is very, very similar to an idea that we worked on in collaboration with Kevin and Jen, in which we are focusing on diphoton and hadronic decay modes of action. But here we are focusing on the muon mode, but as far as the production mechanism is concerned, the story is same as before. So the point is you hit the target with this 120 GeV mu beam, and because of the gluon coupling, you basically get to mix with the standard model mesons that are produced in these solutions. So these guys are mixed interactions, and then these actions can travel a macroscopic distance to your detector and decay into a pair of units. So just a very simple idea. These sort of ideas, they can also be extended in the context of other experiments. So other than DUNE, we can also think about SBND, for example. You can think about both the booster beam and the beam. The BNB, in some sense, is it's basically associated with both SBND and Icarus. and they are basically on axis with respect to the booster beam. But then you can also think about the NUME beam with respect to which SBND and Icarus, they are off axis. But because the NUME beam has a larger energy, you can still get useful sensitivity from that. And then you can try to implement similar ideas in some sense non-neutrino experiments if you want, like for example in either ship or in the context of either. So I won't bore you with all the details here, but let me just skip over to some of the other details of the simulations here. So here what I'm just taking a couple of examples, one for DUNE, another for FASER. So what I'm plotting here are the expected number of signal events you get, given the production mechanisms and the couplings that we have in mind. So here, I should have written, I'm focusing on the case where the electronic coupling is 1/36, so that's the benchmark. And I'm plotting the expected number of events as a function of FA. So for very small FA, the axions, they tend to be short-lived. So you basically have this exponential turn-off. For very large FA, you also get penalized because the axions are long-lived, and you also get suppressed by the production factor. So from that, you expect these lines to fall as 1/FA⁴, which is what you see in these ones. So long story short, you can, for a bunch of different axion masses, you can produce a significant number of dimuon events in the detector. And of course, depending on how much background you have, these sort of cards, they will determine your physics reach. You can repeat the same thing with FASER 2. There also you can produce significantly large number of signal events. And once again, depending on how much backgrounds you have, you can constrain the associated things. All right, so here's a preliminary summary plot. So what I'm plotting is the axion mass on the x-axis and the reach in the inverse coupling, so in 1/FA. And I'm listing a bunch of different experiments. So SBND, Icarus, and Icarus star. By star, I mean it is operating in the context of the NUME beam, so off axis. Then DUNE and also DUNE enhanced. By enhanced, I just mean that in some sense we can also consider decays just before the detector. There is some power because we are thinking about muons. So if you decay even before the detector, the muons have enough energy to penetrate through the heart and travel to the detector. So there is some gain from that. And then finally, shift and phase into. So a couple of important features here. So first of all, of course, I mean, even though we turn off pre-level FCMCs, they're still generated at loop level, and you can basically get constraints from rare meson decay. So do like a k-on into pi-on coupled with a couple of muon search at an F48. You can do something similar in the context of LHCb from rare V decays. However, these searches, they basically operate in a complementary parameter space. So of course, if as FA gets large, you suppress all these searches. The other important parameter space here, or the result here, is a search done in collaboration with Argonute, which we were part of along with Kevin as well. So here, what we did was we basically looked at the Argonute data, and we actually searched for this heavy action into dimuon modes. So here, a very important thing was along like just upstream of the Argonute detector, we also have the Minos-near detector. So using both these detectors, we could feature the background very well, and that led us to basically constrain a new part of the parameter space, which I'm showing in this gray region. And then, along with these two existing constraints, you have all of these projections from these proposed searches. So I should definitely mention that for these projections, I am assuming basically a background research, so like corresponding to let's say 3 signal event. But of course, I mean, this is something that is best verified by the experimenters themselves regarding how much background they would expect. So in that context, these are the curves which are in some sense more useful because they just tell you how many signal events you expect as a function of the action. All right, so
where is your quality correlation line? The quality axion,
good. Sorry, I do not have that plot here. So roughly speaking, I mean, I can show you the plot. I think I actually have some in the backup slide. I'll try to skip to it in a second. But roughly speaking, I think depends a bit on the model of interest. But I think this sort of like if you imagine a line through here, all the regions here would be constrained by the quality problem. So in other words, like as the FA increases, you run into trouble.
So the question is that be okay with that?
Yeah. So I think part of this, so to be precise, we have not done the exact matching, but definitely this part would be totally fine. I do have to go back and do the projection properly to see. My memory is that some little part of this region would be constrained by the yeah.
Question about these dimuon signals.
Yeah.
So I remember stuff we worked on. These axions are so boosted that all of the decay products are going in pretty much the forward direction.
Yeah.
And so I would imagine that in a lot of these cases, you would have 2 muons kind of overlapping.
Yeah.
How do you tell that apart from a single muon signal?
Yeah, so that's a very good question. So I think I think the example we can have in mind is what it is in the context of argonite, right? So there we imagine like you maybe have a single track in the argonite detector itself, but then things separate as you travel the Venus detector.
But Venus was magnetized, which
Right.
allowed them to split apart.
Right. So I think so if my memory is right, I think in the context of DUNE, at least the multi-purpose detector is magnetized. So I guess you would be able to have a similar handle. For these other detectors, I guess, for some of the other detectors, you do have to be a bit careful. So I would say that's why, in some sense, that DUNE would be a concrete benchmark to have. For the other detector, it's probably best to like just do the simulations more carefully and see. Yeah, I think even SHIP also has a magnetized feature.
In FASER, I think.
And also phasers. So yeah.
Okay.
Yeah.
I think it might also be possible that I think this is something we learned from working on these stuff ourselves. Like you could have events where the muons don't start depositing their electromagnetic shower immediately, so you would have a displaced vertex for one muon away from where the other one is. So they might be collinear, but they would have
Okay.
tracks
I see.
that you could use to differentiate.
I see. Okay, that's interesting. Okay. Yeah, that's yeah. So yeah, just to summarize, this is some of the, if you want, theorist level projections. So I think what is super important is, of course, when the experiments turn on, how much background there is, one needs to quantify those. But at the moment, this is what we can do. So with that, let me just conclude. So I have tried to motivate these heavy actions from the perspective of the quality problem, also, of course, from the perspective of the strong CP problem. And I try to show that, or at least illustrate that they also arise in the context of string theory, because you have these extra dimensional scenarios. And then, depending on what FA you have, you can have qualitatively different observables. So first, like if you have gut scale FAs, then the action abundance would be so large that they can serve as a decaying dark matter candidate. It would give rise to these sort of signals in X-ray and gamma telescopes. And for us, I mean, it does give an additional science motivation for pursuing telescopes in that sort of energy ranges. And then for much lower FAs, you can actually produce these actions on shell in various terrestrial experiments, and DUNE or other short baseline experiments, they can have useful sensitivity in constraining the parameter spaces or perhaps even this. So yeah, with that, we conclude, and thanks a lot for all the questions and your attention. Yeah.
Okay, so time for questions.
Got one, maybe related to Vasquez's question. So that sensitivity, those two sensitivity plots you're showing, this one, the one with the beam dump. So the other plot you showed where you're looking at the diffuse gammas, that is sitting way down in the coupling, right below where these are.
Yeah, that's right. That's right. Yeah, because there, I mean, you have gut scale phase, so so this would be like 10 to the minus 14, 15.
Oh.
Yeah.
But if you
Two different scales. So the scale is like this is the TeV scale.
but the band that you were talking about, that's the green band in the other plot.
Yeah, but it is
Yeah.
Yes, yes. So that would run up in fact through some of those.
I don't think it would, so what is happening? So good. So I'm plotting lifetime here. So on the MAFA plane, it would appear a bit differently. So the way to read it would be, so let's say you fix the action mass and you increase the FA. So then this is how you move, right? So this part, I think all of it would be totally invisible in that parameter space because you are at so large a phase.
also for the rough scale.
So the questions? Or any questions from Zoom?
So what's your variable? So
Okay.
you produce lots of variable asymmetry and then cut it down by the degree factor, right?
Right.
That's
Yeah, so
the applet time.
so we actually, so it is not really a flip time, it's very similar to it, but the idea is it is basically based on this spontaneous variations mechanism. I do not have the reference here, but this was worked out by Cohen and Kaplan back in the 90s. So the point is that if you have a coherently oscillating axion, that would generate a chemical potential for fermions and antifermions, and then that would give rise to asymmetries.
Then you cut it down by the.
Then you cut it down. So if you look at the MAFA parameter space, you can draw contours of correct baryon number, and then like there are definitely spaces where you produce the observed one, which is like 10 to minus 10, but you also produce where you also have regions where you produce like three orders of magnitude, and then you can cut it down. So we actually do. I mean, I did not get a chance to talk about this, but we do consider a combined simulation, or if you want cosmological evolution with a very heavy action that does variations for you, and the comparatively lighter but still Canadian reaction that does dark matter for you. And then you do have to take into account, like, if you want to compute the entire cosmology. So if you want, like, in this very heavy action parameter space, like if you focus on the light green region, so in all of this region, that would be mapped onto this lighter action parameter space, which is like this. So in all of these regions, you explain both the dark matter abundance and baryon abundance, and make sure you. Sorry.
Your prediction for that correlated parameter.
Yeah. Exactly.
Okay, any further questions? If not, let's thank the speakers.
Thank you.